Okay, good morning, everyone. This is a continuation of the lecture 6.1, where we listed 4 common point estimators that's used when in certain cases. Okay, they were all related. All of those estimators, as you recall, were unbiased. They all had variances that had n in the denominator, so the variances could go low. So we'll look at those in terms of how good they are. They are good, as well as just some general approaches to discussing goodness. Okay, so the text defines. So first of all, there's 2 properties of the estimator that we've discussed so far, and these are probably the first 2 you discussed. Is unbiasedness or biasness and having a low variance. So the text defines, so these are both good properties, and maybe the two most important. You can certainly see that if you have an unbiased estimator, maybe the next thing you want is low variance, and that if you have both of these properties, you should be probably pretty happy, or you just like to complain maybe. But okay, this is the direction we're going. We're going to discuss how low the variance is, and if look at this in a little more detail today. All right, so the text defines the following. It defines, let's write definition, calls this epsilon here, the absolute value of the estimator minus its target, and it calls this the error of estimation. It's a random variable, right? Because theta hat is a function of the capital YI's. So it's a function of theta hat, and it's random, but it's considered a measure of how well theta hat estimates theta. But we have to make probabilistic statements about it, such as, so example statement would be something like probability epsilon less than b equals, say, like little s or something for some bound. Okay, so this is the kind of statements we can make about it because it's random. All right, so we'll address three cases as follows. The 4 point estimators from the previous lecture all fall into the first case, or possibly the second, but can fall in the first if n is large. Okay, so 3 cases, and all could use this idea. One is theta hat is unbiased. This is true of all from the last lecture, and approximately normal. Also true from all the 4 estimators from the previous lecture, because they were all based on sums of independent, identically distributed random variables. So the central limit theorem gives justification for saying that the estimators were approximately normal. N is not too small. Second, theta hat unbiased, but not necessarily approximately normal or normal. This might be n is too small, or just maybe theta hat is not a sum, is not a linear function of a sum, or so something else, and we can't use the normal approximation. But as long as it's unbiased, we still can make such statements. as up here, using Chebyshev's inequality, or maybe another method too. And then finally, not necessarily unbiased. So in the last case, you might know something not necessarily unbiased. You might still know something about the distribution of theta hat, of the yi's, of the sample, so of theta hat, and be able to make some kind of probabilistic bound like this, some kind of statement as above here. Okay. All right. So in each case, though, this bounding is completely related to the variance of theta hat. Really, you look at the variance, this is also a measure of how well theta hat does in estimating theta. So let's just write this down. So in each, so it's almost equivalent, but it's still a decent way to talk about this. So in each case, the variance of theta hat is what matters, as we will see in our examples, okay? So low variance of the estimator is what we want. Okay, that's all we'll write there. So let's look at case one, and we can look at some of the examples from last time. So say theta hat is unbiased, approximately normal, and this is the case for all four of the estimators from before. So because each of these are sums of IID random variables, we can assume they're normal. So let's just write this again. Theta hat unbiased, approximately normal. This is true of all four estimators from last lecture. Because they were sums. So remember, there was to estimate mu hat. What else was there? So 1, 2, we had y over n to estimate p hat. 3, we had 2 different populations, so x bar minus y bar to estimate mu1 minus mu2. So refer to the other lecture for this again. We don't want to write this again right now. You can ask questions on Monday if you want. And the fourth would be, what the hell? Yeah, sorry, x over n1 minus y over n2, and this to estimate p1 minus p2 when we had the two Bernoulli populations, when we wanted to compare the probabilities, probably to see if one is bigger than the other. So we might be interested in this quantity p1 minus p2, and to estimate it, we would take, again, it's just a special case of 3, really, when the data is Bernoulli. Okay, so the text, sorry. Okay, so in each of these cases, we can assume approximately normal. Okay, so in each of these cases, we can assume approximately normal because you see they all involve these sums of IID random variables. And so the central limit theorem gives justification that they're approximately normal. So then theta hat, in this case, minus theta is approximately, say, still keep writing this for now, normal. The mean is, because theta hat was unbiased, the mean is now 0, and the variance is just the variance of theta hat. We don't know. It will depend on which one we're talking about. So let's just write in this for now. We'll square it because we usually put the variance here, and we'll put theta hat here. So this is just the variance of theta hat, to be clear. Okay, right? You agree with this? Okay, so then if we want to talk about the probability that, say, the error of estimation is less than some bound, b, say, equal to some multiple of the square root of the variance, the standard error, so sigma of theta hat. Well, this is just equal to the probability that theta hat minus theta absolute values is less than k. And since this is normal with this variance here, if we divide both sides by the standard error, this is now equal to the absolute value of a standard normal. We'll write that on a separate line here. So this is equal to the probability that the absolute value of z is less than k. So when the text says find a two standard error bound, it really just means compute b, basically compute sigma theta hat. So when asked to find, or when you want to find just compute b, and interpret, well, it also has to interpret it, and interpret as probability is approximately for this case, when we can assume normality. So you notice then, by just looking up these values, we can make a little table here. So k is, let's say, 1, probability epsilon is less than k times the standard error of theta hat. This is just equal to, or approximately equal to, p norm k minus p norm minus k. And we get 0.6827. We're within 1. 2 is 0.95. Something like this. 3 is 0.9973. I think the next digit's not a 9 for 4. And certainly, right, this is just the area under the standard normal. If I dare try to draw this now, this would be like 0.341. And then what's left over here is, let's say, 30, so 20. I forgot, so 27, 28, something like that. So another 0.13 something 8 maybe here. 0.138. Anyway, this is just what this is. Okay, so the probability that the estimator theta hat is more than k, say, 1 standard error would be the same probability that a standard normal is more than one away from 0. Okay, let's see. Do we do an example? Let's do maybe a quick example here, just to see how this might be used. So as an example, suppose we have y1, say 1600, and say the variance of yi is equal to 9. Where does this come from? It's made up. Okay, so maybe we took the sample variance and used this to assert that the variance of yi is 9. But anyway, we're going to accept this in order to make some progress. And so it's good to always think about that. Where does it come from? Is it actually true? Is it a model? But we're going to just assume that this is true. And so let's say it says find a 2 standard error bound on mu. And interpret. Okay, well, remember the y bar is the estimator for mu that we found last time, so we'll let y bar would be the estimator, so y bar is the estimator. It could say this in the problem, actually. You might say, well, I don't know what to use as an estimator, but let's say y bar will be used as an estimator. If you want, you can put that back into the problem or just say it after. Maybe you're asked to come up with an estimator and say you choose to use y bar. So as an estimator, then we need what? We need to compute 2 sigma of y bar. Sigma y bar is just the actual square root of the variance over n, right? Over n. Over the square root of n, sorry. We've taken the square root already. So this is equal to 3 over 40. Right? And so a 2 standard error bound equals 0.15. Okay, so our interpretation is the probability that y bar minus mu, which is equal to epsilon, is less than 0.15, is approximately 0.95. So for example, if I compute, we'll get to this more soon, but if I actually compute y bar, which we usually call little y bar, so if little y bar, because it means like I actually have numbers in here, is equal to the sum 1 to 1600, little yi, say this is equal to 7. What this says is then we're about 95% sure that mu is within 0.15 of 7. We'll be more specific about that later, that type of sureness. But for now, let's just consider that this is a valid, true probability statement, and you can sort of see how this is going to be used. Okay, now let's continue. We're just going to cover case 2 and leave case 3 till later, the biased case till later. So for case 2, theta hat is unbiased, but not necessarily normal. Well, then we can still use Chebyshev's inequality. So then we could say the probability that epsilon is less than k standard error. This is just the probability that theta hat minus its target is less than k standard error. And Chebyshev says that this is greater than 1 or greater than or equal to 1 over 1 minus k squared. And we can make a little table here. So if k is 1, now before this was approximately equal, now it's greater than. So it's at least this, but not approximately. We just know it's at least, and it's conservative. So here's k, here's the probability, and the first one does nothing for us, but the second one already gets us to 0.75. In other words, we should be 75% sure that we're within 2 standard error of the target, as long as the estimator is unbiased, even if we don't know it's approximately normal. For 3, it's at least. So this probability is greater than, let's say. This, for 3, it would be what? 1 minus 1/9, 8/9, which is 0.88 about, we'll say 8/8 because it's got to be greater. And then for 4, 15 over 16, let's say greater than 0.93. Okay. Okay, so let's just do a quick example, and then we'll stop for today. So example, so say we only have 5. Say we only have 5 samples, and they're IID, Bernoulli P. And we want to find a 2 standard error bound on where y is just the sum. Okay. So again, it's really just a special case of the previous example. So we have that the square root of the variance of y over n is equal to the square root of pq over n, which is, now pq is at most a quarter. It's maximized when p is a half. So we could say already this is at most probably less than, but let's say less than or equal to 1 over 2 square root of n, in this case square root of 5. So 1 over 2 square root of 5, which is approximately equal to 0.22, I think. So for example, so suppose, just an example, that little y equals 3. In other words, 3 of the y's were 1, were say a vote for, and 2 were a vote against, say. Then we would estimate p hat would be 3/5, 0.6, and we are Chebyshev. If you want, you can use it as an adjective here. We are Chebyshev 75% sure the true p is within 0.22 of 3/5 of 0.6. So between 0.82, say, and 0.38, not very good, but it does tell you something. And I mean, think about it, you only took 5 samples. So what do you expect, you know? All right, thank you. That's all for this one. And we'll be back with more to come later.